Okay, so here's our second video that where we'll explain how the body and the kidney will actually regulate water balance and body fluid osmolality. So um, it is all hormonal. So the brain secretes a hormone that will help regulate body fluid osmolality and water balance, and it's this hormone ADH, antidiuretic hormone. It has another name, which is AVP, um, arginine vasopressin. So I'll just put AVP here for those of you who know it by this name. And if it helps to remember, it's secreted from the brain, from the posterior pituitary. And think about it this way. Remember at the end of the last, or in the last video, we were talking about how the body doesn't like to go through cellular shrinkage and swelling, and so the brain is the most sensitive to changes in um, fluid, extracellular fluid tonicity. So the brain doesn't want to shrink or swell, so the brain is the organ that is in charge of secreting antidiuretic hormone. That could help. So there are two main stimuli for the secretion of antidiuretic hormone. One uh, is an elevated uh, plasma osmolality. And so remember, this has to be effective uh, solute. Mainly what we're talking about is sodium. There are osmoreceptors here in the hypothalamus, and these have inputs directly to the neurons that secrete ADH. And as you can see below, um, as the plasma osm increases, antidiuretic hormone, which is here on the y-axis, increases in a linear fashion. And that's due to these osmoreceptors that are sitting here. However, there's a second and also important input here. So the second stimulus is low blood pressure or low perfusion. So baroreceptors in the carotid body and the aortic arch can stimulate through an interneuron ADH secretion. Okay, so and this has been studied. So if there's been a change in blood volume and blood pressure, so once you start having a negative change in blood volume, ADH secretion will increase. And these two, they do work together, such that let's say you had changes in blood volume and changes in the plasmosm. Here's what the curves look like. So here's the normal curve. If there is a change in blood volume on top of changes in the plasmosm, it makes the curve much more steeper. So even if the plasmosm is pretty normal, a low blood volume, low blood pressure, or low perfusion that's being sensed will stimulate antidiuretic hormone, even if the plasmosm is normal. That's important clinically. Um, Likewise, if there's been volume expansion and the blood pressure is normal, this curve is blunted somewhat, in that you will have stimulus for ADH secretion, but it will be blunted if someone's hypertensive or just got a saline bolus, for instance. These two inputs are certainly worth memorizing. Okay, so now we're going to follow antidiuretic hormone and see what effects it has on the body. So just because it's so important, I had to rewrite the two stimuli. So high plasma osm or low blood pressure or low perfusion are going to be the two things that will stimulate the secretion of antidiuretic hormone from the posterior pituitary. So let's do one at a time. So one effect are on V1 receptors in smooth muscle cells located in vasculature, and this will cause vasoconstriction. So this is important that ADH or AVP, so vasopressin, makes sense. It has a vasopressor effect. So this will try and raise the blood pressure, which makes sense. Remember, one of the stimuli was a low blood pressure, low perfusion. So that's important. The other effect is on the cortical and medullary collecting ducts of the nephron. So now we're jumping to the kidney. So in addition, ADH, it goes to the collecting ducts of the kidney, and it acts on the V2 receptor. So the V2 receptor is a transmembrane receptor. Once it's stimulated, intracellular cyclic AMP will increase. Okay. After a few intermediate steps, these vesicles will be stimulated, and the vesicles contain water channels called aquaporins. These vesicles go to the membrane and they fuse, putting aquaporins into the membrane. Okay. So before they were there, remember, water was impermeable. So water cannot pass. These have tight junctions and it's impermeable. But once these aquaporins are in, water can be reabsorbed. Okay. At least they named it a good name, right? Aquaporin, a water pore. We like it when things make sense, don't we? So now water is able to be reabsorbed in the collecting duct as a result of the V2 receptor being stimulated by ADH. Okay. And so I also drew a solute here in the lumen of the tubule. And so as water is being reabsorbed, the urine is becoming very concentrated. Okay. So I'll say here, increased concentration as water is being reabsorbed. And so once water is reabsorbed, it can return to circulation via the vasa recta and the peritubular capillaries. But I hope you're questioning why water is being reabsorbed. Remember, water moves based on an osmolality gradient. So water will only move if this side is more concentrated than the lumen. And so the interstitium is more concentrated than the lumen because, if you remember from the tubular reabsorption lecture, the kidney set up a very concentrated interstitium with a very high osm. And the whole purpose of this is to serve as a strong gradient for the reabsorption of water only when we need it. And we only need it whenever this is being stimulated. And I'm going to show you how we set up that gradient, just to refresh your memory. Okay, so this slide shows what we call the countercurrent multiplication loop and the loop of Henle. So if you remember the loop of Henle, it dives straight down and it takes a sharp turn and comes right back up. This shape is designed, and it's found in other places in nature, basically to establish extreme gradients. And so the kidney uses this shape to establish an extreme gradient in concentration. As you can see, from 300, which is close to normal up in the cortex, to 600 to 1200 at the bottom of the medulla. It does this by dumping sodium chloride, and this is via the thick ascending limb reabsorbing sodium and chloride in an area that does not reabsorb water. So look, here's water. Water cannot be reabsorbed, but sodium chloride is being pumped into the interstitium to make it really concentrated. Urea is also being pumped via the collecting ducts into the interstitium as well. So this keeps the concentration gradient really high in this area. So it's always there and ready. Only in the setting of ADH do we get the aquaporin channels that show up. And so once they show up, now water can freely move out into the interstitium, down its concentration gradient, because the urine by this point is not this concentrated. Remember, another name for this segment of the thick ascending limb and the distal convoluted tubule is the diluting segment, because we're able to take away solute and leave the water behind. That dilutes it back to a normal osm. And so this is normal when it comes down the collecting duct. So if it's 300 here and it's 600 here, water will move, right? And so if it's 1200 here, water will move. And this is how the kidney reabsorbs water. So passive diffusion down a gradient, but it requires making very, very concentrated interstitial osma of the medulla. And so none of this would proceed if this didn't exist. And all this is due to this countercurrent multiplier function of the loop of Henle. When people say countercurrent exchange, that is something that maintains this whole system, right? We can set it up, but you have to maintain it. And that is based on the vasa recta flowing in the opposite direction as the urine flow, which is kind of interesting, but that way vasa recta can stay very concentrated when it goes through the concentrated interstitium, and it can always be available to take up this water. And instead of the water hanging around and diluting out the interstitium, it takes the water and takes it back into the circulation. So the kidney can keep this area nice and concentrated for reabsorbing water only when it needs to. So it is a confusing concept, but these are the key points. You need the concentrated interstitium in order for water to move. Okay, so basically what we're talking about are two conditions, one in which ADH is present and one in which it's absent. So let's consider the situation when ADH is absent. So this is the situation when you just drank a liter of water and you didn't need to. Let's say you're just sitting around studying and studying and studying and drinking nothing but water. You know that you'll be up peeing dilute urine very frequently because you didn't need the water. Water in has to balance water out in order to keep body fluid osmolality normal. So pretty much the default setting of the kidney, at least the part from the ascending loop of Henle all the way out, is to not reabsorb water. That's what this purple line represents. It's impermeable to water. And so when ADH is absent, you will make dilute urine. Okay? Even though the interstitium is very concentrated right here. This is pretty much the default setting of the kidney. All right, so there are those two stimuli. If a high plasma osm occurs or low blood pressure, low perfusion, ADH, otherwise known as AVP, will be secreted. In this setting, from the distal part of the DCT to the cortical collecting ducts, aquaporins will be inserted into the luminal membrane, and now this segment is permeable to water. Okay? In this setting, water will move out as long as there is a concentrated interstitium, and you will make a concentrated urine. And that's what I'm drawing here, a little drop of concentrated urine, where the person on this side is making lots and lots of dilute urine. Okay? So I hope that is pretty clear and can help you sort out the physiology of body fluid osmolality.